Welcome to the office. We want to take a look at one last example for our section on factor group computations. This example is going to actually use the idea of the center, and we do in this example talk about the center being a normal subgroup, right? Implicitly right here. The center of a group is normal, otherwise we couldn't talk about the quotient group. Now, something that I'm going to ask of you in your homework is that you do precisely this. It's a homework problem listed in the book, that is. It can be shown that if G is non-abelian, then the factor group G mod Z of G is not cyclic. We want to use that for this example to show that a non-abelian group of order PQ, where P and Q are primes, has a trivial center. Now, essentially what we can do is we can consider what happens if it's non-trivial. If, let's see here, if Z of G, the center, is non-trivial. So when I say trivial, it's either everything or it's nothing, right? So non-trivial means it's not nothing and it's not everything. So when I say nothing, of course, I mean the identity. The identity always commutes. So to say that it is non-trivial means that it contains more than the identity, but it contains less than all of G. So if Z of G is non-trivial, then the order of G mod Z of G is going to be equal to P or Q, right? It's a finite group, so I can use the idea of the index. And if G is order PQ, then the only possibilities for the size of the subgroup are P or Q. That's it, because the order of a subgroup divides the order of a group. So if Z of G is order P, then the quotient is order Q. If Z of G is order Q, then the quotient is order P. These are our only possibilities for a non-trivial subgroup. However, what this implies that G mod Z of G is what? Well, a group that is of prime order is cyclic and abelian, or abelian and cyclic. Right? Consider the order of any individual element that is not the identity. Well, it's going to generate the whole thing, because if it generated less than the whole thing, then that subgroup would have to divide the order of the group. So that's either 1 or P, or 1 or Q. The option of 1, if it's not the identity, that's not an option. So then it has to be either all of P or either P or Q, which is all of G mod Z of G. So, but this implies that G mod Z of G is abelian and cyclic. But we just said, or what you're going to show is that if G is not abelian, then this is not cyclic. So this implies that this is abelian, and in particular, it is cyclic. Thus, G mod Z of G Z of G is 1 or PQ. And the center must be trivial. It must be everything or nothing. Again, nothing being just the identity element. But that's all that we wanted to show. So thank you for your time and attention. Have yourselves a wonderful day.